Hi everyone, this is Kalyan Kumar and welcome once again to Chemistry Universe. And we are now continuing with alkyl halides. We had done 11 parts. You can go and have a look at all of those 11 parts. And you would need a bit of that to understand this part. This is part 12. And here we are going to talk about the reactions of alkyl halides. And we will also talk about intermolecular and intramolecular nucleophilic substitution. So let's get on with the video. And this is part 12 of alkyl halides. All right, so here we go. The first one coming up is reaction with ammonia and its derivatives. Now, before we start this reaction, let me give you a brief idea what we're going to do in this. We are taking an alkyl halide and we are treating this with ammonia, NH3. Now, ammonia, you know, is a nucleophile and it attacks the alkyl part and the X minus will leave. And for this particular reaction, we will take CH3X as our alkyl halide. And I'll let you know why we are doing this. Now, once that happens, the reaction starts. The nitrogen attacks the CH3 and the X leaves. Now, the nitrogen has already 3 hydrogens and 1 R, and which means it will have a positive charge. And there is an X minus present. That will take the proton away and you will get CH3NH2, primary amine or methylamine. Now, the methylamine formed is actually more reactive or more nucleophilic than ammonia itself. So what will happen is that this methylamine will further react with RX or CH3X and form a dimethylamine, which in fact is more reactive than even the methylamine because greater plus I effect of CH3 and that makes it more nucleophilic, and you will get a tertiary amine, and eventually you will get a quaternary ammonium salt. And I'll just show you how this happens. All right, so reaction of ammonia with alkyl halides produces primary amines, and reaction of alkyl halides with ammonia derivative produces secondary, tertiary amines and quaternary ammonium ions. So let's look at it this way. You got CH3X, you got ammonia. Now what do you expect is you have the methyl ammonium salt and the H plus leaves and you will get primary amine. So let's assume that I initially take 1 mole of this and I take 1 mole of this and assume that only half a mole reacts first. So half a mole of this is left behind and half mole of this is left behind and half mole of this is formed, right? Now what happens is the half a mole of this has an option of reacting with the half mole of this that is left or the half mole of this that is produced. Now this is more nucleophilic than ammonia because of the plus I effect. So what would happen is that the half a mole of this would tend to react with this rather than the half a mole of this. So what we get is that we will get secondary amine. Now again, do the same stuff. Remember you had half a mole of this. Now assume that half of that reacts. That means 1/4 is left. And remember half of this was left initially. 1/4 reacts. So 1/4 is left. And you get 1/4 of this formed. Now 1/4 of this has an option of reacting with half a mole of ammonia that is still left. Or 1/4 of this that is present. Or 1/4 of this that is present. Now this is actually more nucleophilic because it has got 2 plus I effects. So the chance of this reacting with the more nucleophilic nitrogen is again greater. So eventually what will happen is this will react with the secondary amine to form a tertiary amine. Obviously it will also react with the part of this. It will also react with the part of this. So it will react with all of them. So you will get a mixture of all types of products. And then remember this also has still a lone pair. So this can further react with CH3X, even though this is hindered. It's not going to react that fast. But if you take this in excess, it will definitely react with this. And eventually you'll get a quaternary ammonium salt. Now what you need to understand here is that we are getting a mixture of primary amine, secondary amine, tertiary amine, quaternary ammonium salt. And the worst part is none of them are coming out in a good yield. So when we do the reaction, we know this is going to happen. So what we do is we say, okay, it doesn't matter whether you get a mixture. Let us take CH3X in excess. When you take CH3X in excess, meaning ammonia reacts with CH3X, you get primary amine, and there's still a lot of CH3X present to react with the primary amine. Still a lot of CH3X present to react with the secondary amine. Still a lot of CH3X present to react to form a quaternary ammonium ion. So eventually you would get a very good yield of at least the quaternary ammonium ion. You may not get the primary in good yield, you may not get the secondary in good yield, but you will definitely get this. And if you do want to get the primary in good yield, well, take ammonia in excess. So if you have very small amount of CH3X and a large amount of ammonia, the chances of CH3X reacting only with ammonia is greater. So therefore, you will get the primary amine. So either you will get the primary amine in excess or as major, or quaternary ammonium ion is major. And if you take CH3X, the end product that we'll get will always be the quaternary ammonium salt. All right. So let's do a couple of examples. And here I would want you to just revise the Hoffman elimination, because we have done that already, E2 elimination, Hoffman elimination. So this is a tertiary amine, as you can see, and I react with CH3Br. And you know what happens? When a tertiary amine reacts with CH3X, you will get quaternary ammonium ion, remember? So you will get this, A. Now this A reacts with alcoholic KOH to form B. The B reacts with another mole of CH3Br to give C. C again reacts with alcoholic KOH to give D. You have to figure out ABCD. And as is the usual custom, you have to pause the video now, find out all these products, then play back the video to check whether your answer is right or wrong. Okay, let's do this now. Obviously, this is going to be a quaternary ammonium ion. Now, if you remember Hoffman elimination, there we said that if you have a hindered leaving group, you will get a major product as Hoffman, and it is by E2. So what basically happens is, these are the two carbons which are attached to nitrogen. I'm not looking at the methyl carbons because they're not useful right now for elimination, because there's only one carbon in them. So this bond is likely to break, or this bond is likely to break. And in elimination, the H goes from the adjacent carbon, remember? So H goes from here, this group breaks, and you will get an alkene here. Now you can get it on the right side, you can get it on the left side, doesn't matter, you'll get the same product. So what do you think B would be? B would be this. I hope you can understand this. Now again, I'm reacting with CH3Br, so what does it mean? Again, a quaternary ammonium ion. Now only one carbon here is attached that can show elimination. So the H will go from here, this bond will break, the CH bond will come inside, you will get a diene, and you will get Me3N. All right, now let's go for the next reaction. Reaction with aqueous KOH. Now, we have already done this. When we did alkyl halide, when I did the substitution, when I started elimination, in fact, I told you that you can do elimination E2 only with alcoholic KOH. And whereas with aqueous KOH, the concentration of hydroxide is pretty high. The chance of it acting as a nucleophile is far greater. And on top of that, OH minus is not that strong a base to do elimination that easily from an alkyl halide. So you will find substitution happening. So now we are doing reaction of aqueous KOH with alkyl halide, which will simply show substitution. Now what you're required to do in this is, I'm going to give you some examples. You have to find the product and the mechanism from which it happens. All right, the first one is this one. What do you think will be the product? And write down the mechanism. I think this is pretty simple. You have CH3Cl, and substitution will give you methanol, and obviously it will be SN2 because it is methyl. Primary halide, what do you think will happen? If you want, you can pause the video now. You will get obviously ethanol and again SN2. What about secondary? Now secondary, remember, can show both SN1 and SN2. But the medium is aqueous, so SN1 will be a little greater because it can easily form a carbocation relatively to the primary one. You will get the alcohol secondary, and it will be both SN1 and SN2. And if I were to bet, I would say SN1 may be a little higher. What about tertiary? What do you think will happen? This is very clear. This is going to be SN1. What about secondary benzylic? What do you think will happen? Well, Remember, benzylic can do both SN1 and SN2, but being secondary, its carbocation is much more stable, and so it has much more prevalence for SN1 than SN2, and you have aqueous medium anyway, so this will be SN1. What about this one? Now here I don't want you to write the mechanism, I want you to write the product. Now here what happens is, when you do aqueous KOH, both the Cls will be replaced by OH, right? Now whenever, this is called a geminal diol, okay? This is called a geminal diol. Now whenever a geminal diol is formed, they are very unstable. What happens is, one H protonates the other OH. So you can say, let's say this H goes to this O. So what happens is, you get O minus and you get OH2 positive. And then this comes and attacks as a nucleophile, and this goes out as a leaving group. So essentially water is lost and a carbonyl compound is formed. So remember, whenever you have a geminal diol, they are unstable and they will immediately form a carbonyl compound. Use the same logic here and tell me what the product is. Just make the product, pause the video if you want. Yeah, and that would be again a ketone. So let's check the next one. You have 3 Cls now. What do you think will happen? Obviously, all the 3 Cls will be replaced, and 2 of the OH will become a double bond O. You will get acetic acid. Okay, what do you think will happen now? You can pause the video, okay? You can, whenever you want, pause the video now. Now, obviously, it's got 3 halides, but remember, this fellow is bridgehead. It's not going to show the substitution. Only the Cl and the Br will go, and you get a double bond O. And you don't have to wonder whether Cl will go or Br will go, because when aqueous KOH is given, you assume sufficient amount is given. Okay, what do you think will happen here? Obviously, this carbon has 2 Cl, so it will become double bond O. This carbon has a Br, it will become OH. This carbon has a Cl, you will get an OH, but this will not give you any product. So, you will get this. Just check the answer. Then you have this, aqueous KOH. What do you think will happen? Now, remember, this is the aryl halide. And halogen attached to a benzene ring is aryl halide. Aryl halides don't undergo substitution that easily. So with simple aqueous KOH, nothing is going to happen. You'll only get the benzylic one substituted, and you'll get a benzyl alcohol here. All right, let's move on to the next one. This is the reaction with sodium azide, NaN3. Again, it's a very simple nucleophilic substitution reaction. It is Na plus and N3 minus. Remember, this is N3 negative, azide ion. So this is going to act as a nucleophile and replace the X, and you'll get RN3. It's called alkyl azide. Then you have reaction with silver oxide. Let's see how this happens. Now, silver oxide can react with alkyl halides in 2 ways, that is moist and dry. Okay. Now, moist Ag2O gives hydroxide ions. This is used because AgOH does not exist and it must be synthesized in C2. So here the nucleophile is hydroxide ion. So what you have to understand is, in moist Ag2O, it will first form AgOH because it's the metal oxide. It will form AgOH. Now, AgOH is not stable enough to be prepared and kept in the lab. So we create AgOH during the reaction itself, and then it will immediately react. This kind of a situation, whenever something is created during a reaction because it is unstable and cannot form, and when that further reacts, we get, in this particular case, we call it prepared in C2. In C2 means in the situation. So in the situation, it is prepared and then it is made to react. So AgOH is like that. Okay. Dry Ag2O cannot produce hydroxide ion. So in this, the nucleophile is a very strong nucleophile oxide ion, which is O2 minus. So as can be expected, in dry Ag2O, you don't have a AgOH. So the oxide ion O2 negative is the one which is going to act as a nucleophile. Remember, it has got a 2 negative charge. So an alkyl halide is boiled with moist or dry Ag2O depending on what you want. But there's a difference in the product formed from moist and dry. The moist one is going to simply give you OH minus ions, as I said, AgOH, and that will form an alcohol. It is just like reacting with aqueous KOH or aqueous NaOH. But in the case of dry, the nucleophile is oxide ion since it has two negative charge. Now it can act as a nucleophile twice. First, it will attack the alkyl halide to produce an alkoxide ion, which itself is a strong nucleophile. This alkoxide ion then further attacks another molecule of alkyl halide, producing ether. So oxide ion attacks two molecules of alkyl halide. So what you need to understand here is this. You have oxide, O2 negative, and you have Rx. What do you think will happen? O2 negative attacks Rx, X minus leaves. Now one of the negative of O will be lost because it is attacked. So what do you get? You get an alkoxide ion. So first Rx will react with oxide and form alkoxide. Now if there is sufficient Rx, and we do take Rx in excess. So if we have sufficient Rx, now this alkoxide will act as a nucleophile on Rx. So what will happen? It will form an ether because O minus will attack the R and the X minus will leave. So you have a CH3X, you have oxide ion, attacks, X leaves, and you get an alkoxide. Now this alkoxide will react with CH3X and you will get ether. And due to the high concentration of hydroxide or oxide ion, in both cases, nucleophilic substitution is favored over elimination. All right, let's check the other one. Reaction with KCN and AgCN. Now, Rx with KCN gives you a cyanide, alkyl nitrile. Whereas Rx with AgCN will give you RNC, the isonitrile or the isocyanide. Now, there are some nucleophiles which are known as ambident nucleophiles, and this means that they have more than one nucleophilic site. Now, as you can see, in CN minus, you have both lone pairs on C and N, and in fact C is the one which is having minus. So what happens is, in KCN, it is completely ionic, so it will break into K plus and CN minus. And if you keep an Rx there, C will act as a nucleophile because it has more electron density, it's got a negative charge. So C will act as a nucleophile. So you get RCN. But when you take AgCN, now Ag-C bond is not ionic, it is polar covalent. So it takes a little time to break. So meanwhile, as it is breaking, N is still having a lone pair, so N attacks fast. So what happens is, you get RNC instead of CN. So KCN is an ionic compound while AgCN is more of a covalent nature due to lesser electronegativity difference between Ag and C. Therefore, KCN dissociates to give you Cn minus ion, while AgCN the dissociation is poor. So KCN will break easily, whereas AgCN takes a time to break. So with KCN, since the compound is completely ionized, C acts as a nucleophile because of the greater charge density. Whereas with AgCN, the C cannot act as a nucleophile, it doesn't have a lone pair as it is partially bonded with Ag. So N acts as a nucleophile and the major product is AgNC. And the same thing is observed with KNO2 and AgNO2. You have Rx with KNO2 and you will get RONO. And this is alkyl nitrite, and you get with AgNO2, you get RNO2, which is nitroalkane. The logic is same. This is ionic. Remember, minus is on O. So O has higher charge density, it will attack with potassium. Therefore, you get ONO. Whereas in the case of Ag, it partially breaks. So N has the lone pair. So N attacks and you get NO2. So in KNO2, there is a complete ionization. So O acts as a nucleophile due to greater charge density. In AgNO2, there is a partial ionization. So N acts as a nucleophile. Then we quickly do reaction with sulfur nucleophile. And here you will find that you have KSH. You will get a thiol, RSH. Pretty simple. Then we quickly move on to Williamson's ether synthesis. Now this is very simple. Alkyl halide, alkoxide, and you have THF as solvent, and you will get ether. This is same thing that we did with dry Ag2O. First the oxide attacked the Rx and formed alkoxide. In Williamson's ether synthesis, we are taking alkoxide ready-made and making it react with Rx, and it will again give you the same thing, ether. And remember, since we are using THF as solvent, so there is no question of SN1, you'll only have SN2. So we will always make sure that those alkyl halides are chosen which can do SN2. But if you take the same thing in water solvent, you will get elimination. Now, if you remember, I had told you in the previous part, I think, that ethoxide, when it is protonated or solvated by protic solvents, becomes bulky. So much bulky that it doesn't act as a nucleophile, it will only act as a base. So it can only eliminate. But despite being bulky enough not to act as a nucleophile, it is not bulky enough to give a Hoffman product. It will still give you the Sedgwick product. And this we had already done when we did competition between elimination and substitution. Then we have reaction with alkylite salts. Basically, these are salts of terminal alkynes. Terminal alkynes, we can remove the terminal H. You'll get a sodium salt. This acts as a nucleophile. And you get a bigger alkyne with higher molecular mass. And then we do SN2 versus SN2 prime reaction. Now you have alkoxide reacting with an allyl halide. Now this is pretty simple. What do you expect in this? Pretty simple. O minus attacks the C14 and the Br leaves, right? Well, you're right, but there is something else that can happen. You can even get a situation where the O minus attacks this carbon and the pi bond shifts between these two carbons and then the Br leaves, giving you this. Now you may wonder, C14 is at the right side, where did it come on the left side? Doesn't matter how you write it. If you want, you can write it like this, it will be same as this only. Now this is called SN2 prime. So remember, you have to remember SN2 prime whenever you have a allyl halide. So whenever there is SN2 taking place in allyl halide, you will have SN2 competing with SN2 prime. And if you want to guess which one is happening more, well, that is a little difficult to guess because C14 is not actually actively involved. In both cases, the C14 Br bond is being broken. So you cannot guess which is better. And then you have the inter and intramolecular substitution reactions. Now in bifunctional compounds, in which one can act as a nucleophile and the other as a leaving group, intramolecular nucleophilic substitution reactions are favored if 3, 5, 6 or 6 membered rings can form. Now remember, if you have a compound where there's a leaving group and the compound also has a nucleophilic part in the same compound, and it can form a stable 5-membered ring or a 6-membered ring and perhaps even a 3-membered ring, intramolecular substitution is favored over intermolecular substitution. Say for example this one, the N can act as a nucleophile and the Br will leave and you will get a 5-membered stable ring. So intramolecular is favored. Even in this, now if I take this H minus, now what do you think H minus does? Now one may feel H minus will go from the top, attack, Br will leave, H minus is a good nucleophile. Well remember, whenever there is an acidic H and you use a strong base, it will always take the acidic H no matter what. So what happens is you will first get O minus. This O minus being on top and Br at the bottom, it will show SN2 and you will get a 3-membered cyclic ether called epoxide. Okay. All right, let's look at the next one. But suppose if I had OMe, now obviously there is no acidic H, right? So there is only one option. H minus attacks from the top, Br leaves, and you will get 2H on that carbon. Look at this one. If I take NaH, what do you think will happen? Guess. Again, the H minus take the H from OH. It make it O minus and that will attack and form a cyclic 6-membered ether. It's called tetrahydropyran. So there is always a competition between inter and intra. And it is possible that the nucleophile of one molecule may substitute the leaving group of the other. For example, in this case, when we add NaH, instead of intra, you could have inter. It could take H from one OH and this O minus could attack another molecule of this on this carbon, making the Br leave and you get a big molecule like this. Now obviously, intermolecular reactions are favored only at high concentration of the compound as intermolecular distance will decrease. So if the concentration is pretty high, what will happen is that there'll be less solvent molecules between two reactants, and therefore inter is more likely. Secondly, in inter, two molecules are joining into one. Entropy is drastically decreasing. Now, even in intra, entropy is decreasing because of the formation of a ring, but it is not decreasing that much. In inter, it is decreasing a lot. Therefore, since there is a decrease of entropy, will always make the reaction happen at low temperature, because T delta S must not be a dominant factor. So keep the T low, T delta S will not be dominant, and delta H will overtake, and that will make delta G negative enough for the reaction to take place. So you have intermolecular reactions decrease the entropy far greater than intramolecular reactions, as two molecules are combining to form one. So intermolecular reactions are favored at low temperatures. So if I have this, and if I were to treat this with ammonia, well, as expected, it will first remove one bromine and it will give you an H2 here. And then this will show intramolecular substitution. So the N will attack this carbon having the Br, and the Br would leave, and you will essentially get like this. So first you have inter, then you have intra. And that completes our part 12. So part 12 of alkyl halide is over, reactions of alkyl halide. We have two more parts coming up soon, and that will be part 13, that will be the preparation of alkyl halides, and part 14, which is the polyhalides. So we'll be completing that, and I hope we can do it perhaps by the end of this week, both the parts, and that would finish off this lesson, alkyl halides. With that, this is Kalyan Kumar signing off. Have a great day, and thank you for watching this.